All right, next up is my colleague, Nathalie Haurberg from Knox College, going to tell us about science highlights. Nathalie.
Hello, my name is Nathalie Haurberg. I'm an associate professor at Knox College, and I'm going to let you know a little bit about the diversity of research at Macro and give you a sort of catalog of the science highlights. So this is going to be a lot of sort of quick results in a big hurry. And all of these results are featured at our poster session. So I'll just tell you now to visit our poster session. And all of these results are also the results of either classroom science or of student research projects. And this is all undergraduate classroom science and undergraduate student research projects. So the first type of projects I want to talk about are some multi-wavelength astronomy projects. These projects have been done, largely multi-wavelength astronomy done with the VLA and with the RLMT. The VLA projects were gotten, the data was gotten under the Observing for University Classes program. The first project I want to talk about is star formation of the dwarf irregular galaxy Cassiopeia 1. In this project at the top, you'll see an image of the H1 image of the galaxy. And in the H1 disk, you can see that there's sort of a dearth of H1 in the center. There's sort of a hole of H1 in the galaxy. And in the H alpha image, which is taken from the RLMT, from the narrowband images, you can see that there is star formation actually detected throughout the disk by H alpha emission. But you actually see that same lack of H alpha emission in the center of the disk, the same way that we see a lack of H1 in the center of the disk. So we see sort of a dearth of star formation in the center of the disk, the same way that we see a dearth of H1 emission in the center of the disk, which is an interesting result from this Cassiopeia 1, which I should mention is a low mass star forming dwarf irregular galaxy. Another multi-wavelength astronomy project that's been undertaken is a detailed study of the cataclysmic variable STLMI. And so one of the things that we did with the RLMT was detect periodic variability in STLMI. This is a AM-HER type cataclysmic variable, which is a polar. And the periodic variability is almost certainly the orbital period of the polar. So polars don't have an accretion disk. Instead, the accretion is channeled onto one of the poles. And so you're actually seeing variability due to the orbital period and seeing that pole coming in and out of view. And on the far side on the left there, you see an image from the VLA. That's basically just a detection of the source from the VLA. But what we have that's really interesting is we have a simultaneous data set of the VLA data with optical data that was taken at the same time on the RLMT. And so what we're going to be able to do is compare variability in the radio with variability in the optical. That data set is currently being studied, and as was mentioned, it's going to be part of our summer program. But there is a paper that goes more in depth on this system, STLMI, which is really, or sorry, a poster that goes more in depth on this system STLMI, and I highly encourage you to check this out. And I will say a little bit more about it as well, which is that it brings me into my next topic, which is time domain astronomy, which we have a lot of results in as well. So that periodic variability, if you notice, it is very, very periodic. And you can actually do a periodogram fit on it and detect a nice clear period to that periodicity unit. And so there's periodogram fit over it of it on the left. We can do some more time domain astronomy. Some more of the time domain astronomy we can do. For example, we can do asteroid photometry and light curves. We have an example of 321 Florentina that was observed on multiple nights and was observed for more than a complete period of its rotation. So asteroids are kind of weird shapes. They're not symmetric. So you have a sort of large side or a small side. So as they rotate, you get a bright spot and a dimmer spot. So what I have on the bottom there is actually fit over one period where you get the bright spot coming into view and then the dimmer spot and the bright spot back into view and then the dimmer spot, and that's one full period. What's really cool about doing asteroid rotation curves is that if you observe them over long periods of time, you can actually do you can actually do modeling of like what the three-dimensional shape of the asteroid is, or fitting them over long periods of time. We can also do photometric monitoring of optical transients, such as supernovae. And we actually have two examples of type 1A supernovae that were monitored. And they show the characteristic drop-off that you expect for type 1A supernovae, but they show an interesting feature, which is a secondary maxima in the I band. And that secondary maxima in the I band is due to the recombination of iron 3 into iron 2 and emission lines that show up in the I band due to that recombination. And we see it here in supernova 2024 GY. You see the bump, it's just actually in the red line is the I band there. You see the bump in the I band on both of those. And we have another example of it here in supernova 2024 ANY. You see that one really clearly there, that bump in the I band. And this occurs about 20 to 40 days after the maxima, after the original maxima. We have another time domain astronomy example here, which is variable stars. This is an eclipsing binary V1024 Haurberg, which is a not very well studied eclipsing binary. And this is an interesting system where we have very, very comparable eclipse depths. They're actually so comparable that depending on how you determine the baseline, what is labeled as the secondary eclipse is actually deeper than the primary eclipse. So it's very delicate to how you determine the baseline on which eclipse is deeper. But we have a very, very good light curve for this eclipsing binary system. We can additionally detect exoplanet transits. We determined this quite well. We have a very clear exoplanet transit detected here, and there's a poster on that as well. Other than time domain astronomy, we're able to do photometric studies that are not in the time domain as well. And one example of these include doing surface brightness on globular clusters. So this is a project doing fits to surface brightness of globular clusters and fitting King models to those globular clusters. So King models are just a model that fits globular clusters pretty well. It's known to not fit core collapse globular clusters, but for non-core collapse globular clusters, it fits well. And you can derive structural parameters of those globular clusters, such as their tidal radius and what is known as the core radius of those globular clusters. And this is a poster from a poster, and it's about fitting those globular clusters and determining those parameters. So these are basically surface brightness studies that we can do as well. And in addition to photometric studies, of course, we have the GRISMs, so we're able to do spectroscopic studies. So we have all this photometric work, but in addition, we have spectroscopic studies. From the low resolution GRISMs, we have the fitting of line profiles from Seyfert 1 galaxy, NGC 4151. You've actually already seen this profile put up a few times, but we weren't able to just get the profile. We were able to actually do line fitting to the lines and derive equivalent widths of the lines. So this is actually showing you the fit, the line model that's underneath the original profile, and the equivalent widths were fit to these lines. We derived equivalent widths for the lines in the Seyfert galaxy. And using the high resolution GRISM, we were able to do some really fantastic work. So on the left here is a profile from a BE star that is in absorption currently, that we observed in absorption. On the right is from the Catanzaro 2013 paper. This is the same BE star, but in 2013 it was observed in emission. So what we were able to do is observe that this has changed its profile from emission to absorption. And one of the things about this is the H alpha line. I should mention this is the H alpha line. And one of the things that we're able to do is we're able to observe variability in things like the H alpha line. And this was an example of us observing an H alpha line that changed in a BE star from emission to absorption. And that is actually one of the results we got from here, was we got from the results from this that we have H alpha lines that not only did we detect what we expected from BE stars, but we detect a change in the equivalent widths from the H alpha lines, and actually a change that some of them changed from emission to absorption. All right, thank you guys very much.